In the world of data science, the challenge isn't just finding patterns, it's finding meaningful ones fast. With modern databases growing into the millions of records, exhaustively mining all possible patterns is not only impractical, it's impossible. That's where pattern sampling comes in, a powerful strategy that lets analysts explore the most interesting parts of the search space without waiting hours or even days. But here's the catch. Most sampling methods were built for discrete data, think binary item sets, like customers who bought bread also bought butter. When we move to numerical data, real-world values like temperature, gene expression levels, or energy consumption, the rules change. And until now, no method could sample interval patterns from numerical databases accurately, efficiently, and proportionally to their interestingness. Today, we're diving deep into Fips and HFips, two groundbreaking methods introduced in a recent paper by Bekucha, Diop, Wally, Kremelu, and Boisumalt, the first to solve this long-standing problem. Let's start with the basics. What are interval patterns? Imagine you have a dataset of patients with numerical attributes: age, blood pressure, cholesterol, and glucose levels. A traditional approach might bin these values, say, low, medium, high, and treat them as categories. But that's a loss of information. Instead, interval patterns preserve the full numerical precision by representing a pattern as a vector of intervals. Age, blood pressure, cholesterol. An object, a patient, is said to occur in this pattern if all its values fall within the corresponding intervals. The frequency of the pattern is simply how many patients match it. And its hypervolume is the product of the lengths of each interval, essentially, how spread out the pattern is in the data space. Now the core challenge. How do you sample interval patterns so that more interesting ones, like those with high frequency or large volume, are more likely to appear? Naively, you could generate every possible pattern and weight them by frequency. But the number of interval patterns grows combinatorially. For just 3 attributes with 4, 5, and 6 distinct values, you get over 1,500 patterns. With more attributes or more values, it explodes. So we need a smarter way. The key insight, sampling via objects. Fips and HFips use a 2-step sampling procedure, but instead of sampling patterns directly, they sample objects' data points first. Why? Because every pattern covers a subset of objects. So if we can compute how many patterns cover a given object, we can use that to bias our sampling. Enter NIP, the number of interval patterns covering an object. For a single attribute, say age, and a value like 42, how many intervals include 42? All intervals where the lower bound less or equal to 42, and the upper bound greater or equal to 42. So if the distinct values in age are 30, 35, 40, 42, 45, 50, then lower bounds, 30, 35, 40, 42, right arrow 4 choices. Upper bounds, 42, 45, 50, right arrow 3 choices. Total intervals covering 42, 4 times 3 equals 12. Multiply this across all attributes, and you get NIP, G, the total number of interval patterns that cover object G. This is critical. NIP, G, gives us a proxy for how popular an object is, and thus, how likely it is to be part of a high-frequency pattern. Fips, sampling proportionally to frequency. Fips works like this. 1. Preprocessing. For each object G, compute NIP, G. 2. Step 1. Draw an object G with probability proportional to NIP, G. So objects covered by many patterns are more likely to be selected. 3. Step 2. Construct a pattern covering G by sampling for each attribute. A lower bound uniformly from the set of values less or equal to V sub G, M/sub. An upper bound uniformly from the set of values greater or equal to V sub G, M/sub. The result? The entire pattern is sampled proportionally to its frequency. Why? Because the probability of drawing a pattern V is equal to the sum over all objects G in its cover of. The chance of picking G proportional to NIP, G. The chance of building V from G, which is 1/NIP, G. These cancel out, leaving us with a final probability proportional to freq, V. And the maths? It's exact. No approximations. No assumptions. Just rigorous probability theory backed by formal proofs. HFips, adding hypervolume for better patterns. But frequency alone isn't enough. A pattern could be frequent but trivial, say age, which covers everyone. It's not informative. That's why we introduce hypervolume, the product of interval lengths. A wide pattern is more likely to be meaningful, especially in high-dimensional data. So HFips samples patterns proportional to the product of frequency and hypervolume, freq, V times vol, V. To do this, we define a new function, if G, the sum of hypervolumes of all interval patterns covering object G. How do we compute that efficiently? We use the total interval length, TIL function. For each attribute, we compute the sum of all interval lengths that contain V sub G, M/sub. This is done by summing all upper bounds, multiplied by the number of lower bounds, minus the sum of all lower bounds multiplied by the number of upper bounds. For example, if V sub G, M/sub equals 42, and possible lower bounds are 30, 35, 40, 42, upper bounds, 42, 45, 50, then TIL equals 42 plus 45 plus 50, times 4 minus 30 plus 35 plus 40 plus 42, times 3 equals 137 times 4 minus 147 times 3 equals 548 minus 441 equals 107. Then if G is the product of TIL across all attributes. Now in HFips. 1. Draw an object G with probability proportional to if G. 2. Then for each attribute, sample bounds with bias. Lower bounds favor smaller values, which allow wider intervals. Upper bounds favor larger gaps B-A. This ensures that patterns built from G are both frequent and wide, capturing the most informative, high-impact regions of the data. And again, the math holds. The sampling distribution is exactly proportional to freq V times vol V. Why this matters, the long tail problem. In traditional sampling, especially uniform sampling, you get a classic long tail problem. Most patterns are uninteresting, low frequency, and trivial. You end up with 99% of your sample being noise. But Fips and HFips avoid this. Because they're biased toward objects that are covered by many patterns, they naturally focus on the head, the high-interest, high-frequency, and high-volume patterns. In experiments across 13 real-world databases, from medical records to energy consumption, Fips and HFips consistently sampled patterns with much higher frequency and higher frequency times volume than uniform sampling. And crucially, they delayed the long tail dramatically. For instance, in the cancer dataset, 99% of uniformly sampled patterns fell into the low-frequency tail, but only 15% of HFips patterns did. That's a game changer for analysts who need to explore meaningful patterns quickly. Diversity versus efficiency, a trade-off. You might wonder, are these methods too focused? Do they lose diversity? The answer is nuanced. Fips and HFips produce patterns with higher frequency and coverage, so they naturally cover more objects. This leads to higher diversity in equivalence classes, different sets of objects covered in most datasets. However, they also increase coverage overlap. Because they sample patterns that cover many objects, there's a higher chance of overlap. This is visible in Jaccard index plots. HFips patterns are more similar in coverage than uniform ones. But here, as the trade-off, diversity isn't the only goal. In interactive mining, you want high-quality, informative patterns, not just random variety. HFips gives you that, while still maintaining good diversity in the types of patterns you see. And speed. Fips is fast, sub-millisecond per pattern on average. HFips is a bit slower due to the weight computation, but still under 10 milliseconds in most cases. Uniform sampling, by contrast, is slower because it must repeatedly check coverage to avoid empty patterns. Plausibility, are the patterns meaningful? Finally, we ask, are these patterns actually plausible? We use a standard plausibility test. Compare the frequency of a pattern in the real data versus in a randomized version of the data, where values are shuffled. A truly meaningful pattern should appear much more often in the real data. As expected, uniform wins on plausibility, because it samples rare, non-overlapping patterns that are unlikely to appear in random data. But Fips and HFips, being biased toward frequency, sample more common patterns, which do appear in random data, so their average plausibility is lower. But here's the key, plausibility is not the only metric. If an analyst is exploring for high-impact patterns, they want frequency and volume, not just rarity. And Fips and HFips deliver that. Moreover, they require far fewer draws. To get 10,000 patterns in a given frequency range, uniform might need 10 to 100 times more draws than Fips or HFips. That's a massive efficiency gain. The bigger picture. Fips and HFips aren't just incremental improvements. They're paradigm shifts in how we interact with numerical data. They enable interactive mining, instant feedback on pattern quality, bias-aware exploration, focus on high-impact regions without manual filtering, scalable discovery, no full enumeration needed, explainability, patterns are interpretable with clear bounds. And the future? We can extend this framework to sample patterns that satisfy user preferences, like find wide patterns with high frequency and moderate volume, or to incorporate other measures like density or coherence. Even more exciting, using sampling to guide hyperparameter search in machine learning, directing the search toward informative regions of the parameter space, reducing training time and improving model interpretability. Final thoughts. In a world where data is vast, complex, and growing, we can't afford to mine everything. But we can mine the right things, efficiently, accurately, and with purpose. Fips and HFips give us the tools to do just that, for numerical data, with full mathematical rigor, and without sacrificing speed or quality. This is pattern sampling, evolved. And it's just the beginning.